one or two German machines, whose names escape me at the moment.
Okay,
But
we're ready to roll now.
there weren't very many of those in this country. And of course, anything that was made in Germany, we didn't have any chance of acquiring during that war. But a Scandinavian machine we might have. But fortunately, I think it was fortunate, why the manufacture of desk computers had been pretty largely converted to this country. The Americans didn't depend on any other country for their calculation equipment. They did depend, I guess, in some ways for strategic chemicals and dyes and other things of that sort, you know, but there wasn't any dependence that I was aware of which affected our computational ability. We could get everything we wanted, provided the wartime boards and priorities and so forth could see your request as one that ought to be taken care of. But it's pretty clear to a military man, of course, that you've got to have fuses to make those shells explode. What good's shooting the shell over there if it doesn't go off when it hits? You know? So it's just like firing tables. This is a real important thing, and without which you don't get anywhere. And so it's hard to tell which is the most important thing. If you're short of gunpowder, well, then you've got to be sure you give priorities to get more gunpowder, and so on. So some of my friends, whom I mentioned a little while ago, who were at the Department of Terrestrial Magnetism doing the work on atomic fission just before, about the wartime, transferred over to the Johns Hopkins Applied Physics Laboratory, which they set up in Silver Spring, Maryland, and they, together with the Bureau of Standards, worked on what's called the proximity fuse. The proximity fuse was a way of exploding a shell when it got close to its target without ever having to hit the target. And that, again, of course, was done by a kind of radio. So the shell could sense that it was close to an airplane, say, and explode close enough so it did a lot of damage to the airplane and perhaps to the pilot without ever having touched that plane, to know that in the way an ordinary old shell would know by having its nose hit something solid which pushed against it, you might say. And so just being close to it, that made a big difference, for instance, in the mortality of the enemy's planes and the effectiveness of the anti-aircraft fire. Just coming close, being able to knock them down. Well, there were all sorts of different activities competing during the war then for manpower and for equipment, whether it's calculating machines or vacuum tubes or what. And into all of that, we had to be one more competitor, you might say, to try to get people who were adequate to do what we wanted to do, and vacuum tubes and other things to implement the actual hardware. So, in addition to Sharpless, of course, one of the first things we did was to say, certainly we can have Burks, can't we? Well, yes, we could, you know. And so here was a man who had been trained in logic, and we recognized that there's going to be a lot of hard logical thinking about how these circuits go together and testing them out and so forth. And on down the line, we got a few people from RCA, for instance, a man named Chedaker, who had been building test equipment over there, I believe, and who came and helped build our test equipment because we had to have equipment to test what we were doing. And then there was Jack, I've forgotten his name now, who now works the Naval Ordnance Naval Development Laboratory near here. But he was one of the first people we could get where we could put on testing out the basic counters, which are the essence of what I'd been thinking about all these years with taking the cue from the cosmic ray work. If you could count these pulses, then you could do arithmetic with them and therefore do all kinds of calculations with them. And Jack Davis, his name is. And so I'm not sure I can name them all right now, but we built up this staff rather quickly and out of people that I'd never met before. They were, as I say, quite often the people who were either friends of Professor Eckert directly or people who had graduated from the Moore School and were known to the various professors around. So in the course of not too long a time, then we had about 12 engineers who were ready and willing and capable, and all they really needed was to be given the guidance and direction. Tell them what is it we're going to try to do and by what rules are we going to proceed so that we all work together and don't waste our effort in devising and designing the same thing 2 or 3 times. It's the essence of a thing like a calculating machine that there will be many parts of it which are the same. In other words, there's a lot of repetition in it. In an ordinary mechanical calculating machine with gears in it, why, if you're going to handle 10 digits, why, you need at least 10 such gears. If you're going to multiply 10 by 10, why, you're going to have something that receives the product with 20 or more such gears, every gear of which is exactly alike. Well, the same way with the electronic machine, the analog that we were building is an analog only in the sense that it's like or similar to, but we're still talking here about a machine which counts digits. So we're not talking about an analog machine in the way I was using the word analog before. The similarity here between the ordinary mechanical computers and our electronic one is that in both cases we were going to handle digits, and you're going to have a lot of digits to handle, so the component pieces which are going to handle this digit are just going to be the same thing as handle that digit and another digit and another digit. You're going to build a lot of equipment which is exactly the duplicate of what's ever sitting next door to it, you might say, in the same big framework. So that basic building block that we had to start out with was what we called a counter. And we decided at the very outset that we would make this machine be a decimal counter, use decimal counters and work on a decimal principle so far as anybody observing its action is concerned. What they would see and what they could read out would be decimal numbers. This didn't mean that we were unaware that the binary numbers existed. That'd been known in mathematics for a long, long century or so, you know. Nor were we unaware of the advantages of using binary numbers in calculation. But those advantages are advantages to the equipment, not to the human being using it. And we knew that being the first ones to embark on a calculating device which is going to work very fast, that we've got to make it so that it cooperates well, you might say, with the human beings using it. And so it's up to the equipment to be readable in human terms, and the simplest thing for the human being can do, the simplest thing he can have is something which speaks directly, you might say, in the decimal system, so that he doesn't have to worry about converting from one system to another, but it's already in the system that he has been used to using, and everything else around him is using it. All the punch card equipment at Aberdeen would take in decimal numbers, punch decimally into cards, and put out decimal numbers printed on pages. So from the user's point of view, all that calculating equipment that they used in punch card room was decimal, just as all of the desk computers that they used were decimal. So we made ours decimal too. That's just a matter of good sense, we thought, to make it speak the same language for the first one at least. Maybe later it would be all right to go to something else. But it still stands that the reliability, which was a very important part of all this, depended upon having the inner workings of this machine ultimately come down to on-off switches, which means you're using binary methods. You're not trying to measure whether a current is 2/10 or 8/10 or 6/10 or 9/10 of some standard, but every current, every signal in that machine then can be stated right away. It's either an on signal or it's an off signal. Or to speak in mathematical symbols, well, you could say it's a 0 or a 1, which are the only two digits then in what is called the binary system. Many people get carried away nowadays, of course, with the fact that because of that essential binary requirement, which is put on us primarily for reliability reasons and only slightly for reasons of efficiency. That is, you don't reduce the amount of equipment much by making things binary. Some people argue that binary is the more efficient, and in some ways it is. But that is the primary consideration. The primary consideration is the reliability. And many people think that because they've heard that somehow you've got to have binary this and binary that whenever you get near an electronic computer. And of course the real essence of how humans can use things is to have the computer speak their language. And so it always happens that any computer you use, then or today, is ultimately going to have to use whatever is appropriate to the problem you're solving. In accounting and many other problems, many of the scientific problems, the decimal system is what you want. There are some problems where the binary is what you want. Well, take your choice, but it's the job of the computer to translate and the human being to interpret. So you make the interpretation as easy as possible by making the machine do the translation to the easiest system. Well, that's a sort of a side lecture, you might say, on where that binary system came in and why we were working on decimal counters at that point. It was just a choice of ours that the decimal system was going to be the easiest for people to use first, and we had no argument on that point from Aberdeen. One of the first things, of course, when this contract did get into effect was that people like Dr. Leland Cunningham, an astronomer who was working at that time at Aberdeen, as were other astronomers and mathematicians, helping the Ballistic Research Laboratory in their computational work. Dr. Cunningham came up and consulted with us, and we went down there sometimes and consulted with him over just what number system should we use, over how many digits we should have in a package which we called a number. So how many digits? Well, if they're decimal digits, we finally elected as a reasonable package that 10 decimal digits would constitute the biggest number that we would normally want to deal with in our computations. Not that this was good for all time, but that many things could be done with less than 10 decimal digits. And if we wanted more, there are ways of, you might say, arranging this, fabricating bigger numbers out of 10-digit numbers. And that's true even today. You notice the little calculators that we can buy for $5 or $10 are usually either 8 digits or 10 digits in their amount of accuracy to which they work to in a little handheld calculator. But at that time, it was a decision for the work of the Ballistics Research Laboratory, who had many problems, including the firing table problem, what would be the best choice. And so we made the choice that it would be 10 digits per number. And then there's the question, well, how many such numbers do you need in a machine at one time? Of course, if you need different numbers at different times, well, that's just a matter of feeding things in and out somehow. But the essence of big calculations usually is that you're going to be dealing with a number of such numbers or quantities, and you've got to have them available quickly when you want them if you're going to make any speed at all in the total computation. Well, I'd estimated in this August 24 memorandum that I'd written, and which was the first basis for Goldstein's interest in this ENIAC project, and which was quickly followed, of course, by the more detailed proposal of what we were going to build. That estimate that I'd written, the proposal I'd made, depended on some estimates which said that I thought that we could use pulses and count pulses at rates which might be at least 100,000 per second, because the people at cosmic ray work and such were doing better than that. Why, with reliability, we might hope to do that well. But could we do that well? Well, to be sure, that was where the first job came when we started in. The job started, from our point of view, on Eckert's birthday, April 9th. This was 1943, although the university's contract, the formal contract, started on June 1st, I believe. So we started off here, assembling the staff. What are we going to do first? We're going to find out whether we can build a reliable decimal counter. Well, there were 5 or 6 different types of counters which were already in the literature, some of them from cosmic ray work and others from maybe other laboratories, but possibly stemming from the same kind of nuclear research work where somebody wanted to scale down the rapid rate at which these pulses were occurring in their experimental circuits. And so there were a variety of ways in which people had said that they thought that this was a good way of doing it. We also had access to a method which was being used at RCA, and one way we had access to this was that as soon as we got wind that the project was on, you see why, then Goldstein set up requests for having us visit the nearby RCA laboratories to see what they were doing in electronics, which might be of help to us. And so in those laboratories we saw some counters which were used essentially for timing things, chronographs, as you might call them. So between a certain pulse electrically produced by maybe a bullet being fired from a gun and another pulse which was electrically produced by the gun going through an induction ring or hitting a target or whatnot, between those two pulses, how much time elapsed. Well, it would be in very small fractions of a second. If the bullet was any good at all, it was going fast, and you try to separate these two things that you're measuring, but the bullet's fast, and to get accuracy in the velocity of the bullet, why, you had to have these timers which operated in better than milliseconds. And that's what one of the things that RCA was building, counters which would do that. So we tested their circuits to see what kind of a counter they had. And of course, our test was focused on primarily how reliable is that counter. Will it work all the time, be accurate to the single counts? How fast will it count? And these are all interrelated questions, because a counter can be very reliable at slow speeds and just go all to pieces, so to speak, and fail at some high speed. So you've got to somewhere draw the line where you say it works very well at this speed and it's lousy at that speed, so we've got to make a choice for that counter. Where would we be able to operate it? Well, as far as we're concerned, of course, we didn't want anything to fail any time. That's always the absolute requirement on accuracy. No mistakes. Well, that's a fantastic requirement, just as the electric companies are trying to explain at the New York blackout right now. Nobody can guarantee that it won't happen again. You just try to make it as unlikely as possible. So we were running these counters from pulse sources which would try them out at 10 per second, 100 per second, 1,000 per second, and 10,000, 50,000, 100,000, 200,000, and if necessary up to 1,000,000 or so. Practically any counter we tried was out of the picture, you might say. When you got up to 1,000,000, it made too many mistakes. And so question, of course, of not just taking the designs as they had been given to us, found in the literature or handed to us by someone, but is there any way we could see to improve them? And here was one of the first things which Eckert did in making a big contribution as far as I was concerned. Not only the overall picture of the reliability, but he put his finger on some things which were in all of the circuits which had been used and proposed by other people, and said, if we can just change that, why, that would make a big difference. And so he utilized what we call feedback to ensure that in a decade counter, that is a counter which counts through 10 and cycles around every time it reaches 9, while the next count is called 0, and it goes from 0 up through 9 and back again and so forth, giving out appropriate carry pulses to tell some other counter to count tens or hundreds and so on. In such a counter, one of the defects was that sometimes two different tubes would be on at the same time, which is an ambiguous indication, of course. The counter is not supposed to say, for instance, 2 and 7 at the same time. It's supposed to say 2 or 5 or 7 or something else. But it's always got to be unambiguous. It's got to be clear each time what position it's at in counting. So if a counter has the possibility of having two indicator tubes on at the same time, can this be prevented? Well, if it can't be prevented, well, there's something really bad about this, you see. You mustn't tolerate that. And so people have been trying to do that apparently with minor adjustments here or there and so on, and saying, well, if this counter's failing, why, perhaps we ought to change this resistor a little, or we ought to change that condenser a little, that capacitor. And so he said, well, if we just put in a certain kind of a feedback circuit which makes it so that it cannot have more than one of these stages on at the same time. It will itself, you might say, have an action which prevents any other of the stages going on at the same time. And that made all the difference, really, as far as the reliability is concerned. And I remember years later when we were up at a conference someplace, and there were still people who were using counters in their nuclear experiments. Were saying, I don't see how you got that ENIAC to work with all those counters in it, because our experience is, this is present tense for them, you see, our experience is, this was years after we'd made the ENIAC, that these counters have to be readjusted and we have to send them back to the shop to be fiddled with every week or so. And we have this trouble and we have that trouble and so forth. We tell them about this feedback thing. Oh, never thought of that. So anyway, that first step was taken. That is, that Jack Davis and some other people working on a test bench under Eckert's direction modified the various counters, ran the frequencies up and down, and so on. The second thing we did was to, and I say we, I'm just talking about this as if we all had a hand in it, but this again was not my part, it was some of the electrical engineers, and Eckert's adequate direction of how to do these things efficiently. We decided that just how well the counters responded depended on what shape of pulse they were fed, as well as how big a pulse or how small a pulse or how fast a pulse. And so one of the things that went into our counters, which you wouldn't find in many of the other counters, was a preliminary circuit called a pulse shaper. So that no matter what kind of an electrical signal came into this counting circuit, that what was fed to the thing it was actually supposed to advance 1, 2, 3, 4, so forth, as pulses came along. The signal that went to them was always of the same shape. It went up, but it went down, but it didn't go ziggling around in between. And it didn't go up faster than a certain amount or come down faster than a certain amount. It did a sort of standardized job, so you could call it a pulse standardizer if you wish. And part of the standards, of course, that Eckert set up right away were that all the pulses we would deal with in this calculating machine would be standardized as regards their height, that is, how much voltage they occurred, as well as that shape that we're talking about. And so you wouldn't have to say that in this thing over here the pulses are weak and therefore they don't do as well. And over here in another place, why, we've got very strong pulses, so we should design the circuit differently because we don't want it to respond too soon to those strong pulses or something. Instead of having a lot of disorganized different things, you might say he did for the pulse industry what the first gun manufacturers might have done and credited with doing in the mass manufacturing, of course. They standardized parts so they were interchangeable. So the various pulses we were dealing with in this machine had to be interchangeable in that sense. They always were within a certain tolerance. The tolerance was wide. In other words, we set limits and say, well, the pulse has to be acceptable if it's above, say, 6 volts and below 12 volts. Any time in that range, 2 to 1, say, is satisfactory. And everything that we're working on should respond correctly as long as the pulse is within that range. Well, that's not a hard range to meet, you see. It isn't as if we were the telephone company trying to send signals all over the country, and different places we had different needs for amplification and so forth. That would be a much worse problem, which they have to meet in their own way. But we could standardize all this equipment in the same room and all being designed by the same group, that this was the way it was going to be. Well, by setting up those rules in advance, this is the way it's going to be, and no matter whether there's one engineer designing this circuit or 12 engineers using it, all of us as a team count on that fact, that the pulses that some other part of the machine send to my circuit will be within these limits, and I don't have to design for anything except pulses of that size, shape, and so forth. And that's the way my machine, my part, will be tested. It does work within these limits, and it doesn't have to work outside of it. So with a lot of standards which could be written down and were written down and were circulated and handed to all the engineers at the time, they were given notebooks that said, this is what you're going to do, and this is these are the rules for getting together and how everything cooperates. Well, then, of course, the next question was the logic of the individual components, because we did have to, first of all, say we're going to add numbers, subtract numbers. We also said we had to multiply numbers. We're going to have to divide numbers. And, of course, it was a matter of taste, you might say, as to whether we did anything more. But this taste was aided by the judgments of Dr. Cunningham and others from Aberdeen. And it was decided that we should have what we call function tables, which would give out values of a function when they were told what the argument to that function would be. As an example, if they wanted to have a standard device which would create square roots, why, they could say, well, here's a number I feed to this equipment, and it's going to calculate the square root. Well, how would you do that? You could do it by calculation, which is the way we actually did it. But we could have had a function table which said, within this range, why, the square root of these numbers is a certain number. And so it was decided, for instance, that a function table would be very useful, first for mathematical functions like sines and cosines, the trigonometry of the problems of the ballistic firing tables, for instance. Why, you have to know what vertical and horizontal components there are to the path of that shell, because gravity acts vertically, and wind resistance acts in different directions depending on the direction of the velocity of the shell, and so on. Why, so sines and cosines would be very useful. So if we fed into a function table a certain angle, then we'd like to know the sines and cosines to get the components. Well, at first, I think they decided they'd only need 2 function tables, and later they decided they need 3. And there were other decisions like that where the amount of equipment which we were going to build got upped later, after we'd started off on the design and gotten pretty much thought out as to how we were going to build these various modular pieces. Then a little extra thinking on the part of Aberdeen was to the effect, well, maybe 3 function tables would be good. Maybe 20 accumulators would be better than whatever they thought they might need at first, and so on. The accumulators were the numbers, that were the units that both stored and added and subtracted. Well, some of those accumulators also were standard adjuncts to our process of multiplication and division and square root. So actually, of all of the 20 accumulators which we finally put into that machine, most of them were associated with something else when they were needed for that purpose. Some were associated with the divider, so as to hold the quotient and the dividend. And it took all together 6 accumulators, I believe, for the multiplier. Because, first of all, if you want one accumulator to hold the multiplier and another the multiplicand, the two factors. That took two accumulators just to start off. They were storing the things to be multiplied. It would take at least two more, of course, to store the product. If you multiply two such 10-digit numbers, why, you're likely to get a 20-digit number. But to get the speed we wanted there, why, I was utilizing that principle, which I'd already seen mechanically in the Remington Rand punch card equipment at the World's Fair. The principle of first getting partial products of all the digits and then adding them together at a last fell swoop, you might say, which speeded up by a factor of 3 or 4 or 5 the rate at which you could do multiplication. And so in that case, why, we had to have a duplicate 20 digits, one of which was holding the sums of the right-hand part of the product of two digits, and the other was holding the left-hand part of the product of two digits. And then only after all of those things had been put together were these two combined in such a way as to produce the final product. Well, we were sort of speed demons, you might say, there, because we had advertised the idea that we could immensely speed up the process of solving differential equations and such things for Aberdeen with electronic devices which worked with digits. So we thought it was incumbent on us at that time to make these things run as fast as we could. You might say, well, we could have speeded them up by trying to get a counter which counted twice as fast, and everything would work twice as fast. Well, it isn't quite the same argument as the one we made with respect to the differential analyzer, where I said if you run that twice as fast, why, everything wears out faster and you have a hard time keeping an adjustment. Here, things don't wear out faster when you run at twice the frequency, but the reliability begins to be doubtful. And so what we'd picked was that we had counters which would probably run at counts of 200,000 per second. Often they did under test, but that to be safe, we would standardize and everything would work at 100,000 per second, and we would put in a pulse generator sort of gadget which would allow us to operate at lower or higher speeds just to test how it behaved under those conditions, even when the machine was all finished. Why, we could plug in this thing and we could run it up to 150 or 200,000 pulses per second and see if anything failed. This is a good test method sometimes to see where's the weakest link, just like you do in testing materials. Why, you might say very literally, you might take a chain and stretch it under that stress. Which link is it that breaks? And that's the one that you've got to strengthen. So we had these various ideas as to how we were going to test this and how we were going to get the reliability, all of which were pretty much had to be thought out right away, you might say, in the first month or two. Why, a lot of this had to take shape, and in those few months in the beginning, why, we were daily meeting with these various engineers and telling them, this is what we're going to try to do. Here are our standard methods of trying to get the reliability and getting, of course, the efficiency of design, so that if a circuit, which we call a flip-flop, which would go on or off, is going to be used all over the machine, we don't want each of you engineers designing his own idea of what he thinks the best flip-flop is. We've designed one, we've tested it. This is the flip-flop that everybody's going to use, unless there's some good reason that he needs something different, in which case, see Eckert and we'll work it out, you know. And so, in most of those situations with regard to the electrical design, why, it was eventually a matter of seeing Eckert. He had the advice and the ultimate approval and all those things. On the question of what the machine was supposed to do, well, I had a big hand in that, of course, together with the discussions with Cunningham and Eckert and others as to just where there were possible things, like should we have 10 digits or 12 digits or what. Well, of course, that was a matter of judgment, not a matter of whether it would do something or not do something, but rather what's the best place to standardize in the mathematical side of it. And at the very beginning, of course, people were saying, but these differentiations and integrations and things that you're going to do mathematically, theoretically in calculus of the mathematics, where you have continuous variables, why everything is infinitely accurate. But you're going to approximate all this stuff with digits, and the digits have to be chopped off at some point. So you're saying 8 digits or 10 digits, and the really accurate number would be many, many more digits long, if you could ever make it long enough, like the number pi, for instance. It takes an infinite number of digits to represent it exactly. And the symbol pi doesn't do you any good if you're making numerical calculations. You've got to put a number there. And the shorter the number, the less accuracy you have. So as you compound these things, you multiply them, divide them, and so forth, why there'll be inaccuracies all the time. So whatever methods you use when you're trying to do continuous problems with digital discrete variables, you're in trouble. What are we going to do about that? How much do we have to account for there? Well, nobody knew exactly. I had some ideas because I'd done some of the work on numerical integration before. The Aberdeen people, of course, had lots of ideas from the way they were doing their firing tables, which were all numerical integration, and the way they checked them. Everybody had some idea, but we wanted this to be a general purpose calculator, not just do firing tables, but whatever scientific jobs that the ordnance people might have. And among those jobs, for instance, were what they call interior ballistics. What is the phenomenon of the powder burning inside the gun bore? That has a lot of influence on how that shell eventually gets out of that gun barrel. Is the powder burns fast or slow? Something like the phenomenon in your automobile of do you get a knock when the gasoline explodes? It has to burn a certain way. And there's a lot of internal combustion engine research is devoted on how do you shape the chamber, how do you do this, how do you do that, what kind of fuel do you use, and so on, in order to get the best efficiency out of just exploding some gasoline inside of a cylinder, pushing the piston. So all these problems of internal ballistics were part of Aberdeen's problem. And it became clearer as we learned Aberdeen had a wind tunnel, not for airplanes, but for the shells themselves. They had to know how much air resistance there was, and how do you design an artillery shell so that you get the longest flight possible for a given charge in the shell, a given type of gun, and so on. You want the biggest range you can get. Now, what do you do to the front of that artillery shell to diminish the air resistance and to make it fly true also? So if the shell wobbles, why, it may go off target just because the air resistance is shifting, and sometimes it's on one side and sometimes on the other. So the wind tunnel down at Aberdeen was continually studying the shapes of shells and what the air resistance was, and making what they call Schlieren photographs, which used the diffraction of light, which would show the pressure, the occurrence of the different pressures around the shell as it would be subjected to a wind speed within the tunnel. Well, all that data had to be reduced from the measurements, and all that data presumably someday would be subject to scientific calculation, have a theory for it. and say this shell is better than that because the theory shows that it will be, and so on. All those different things were proper subjects for the Ordnance Laboratory, the Ballistics Research Laboratory at Aberdeen, to be working on. And it was their requirement from the very start that the machine that we would build was not just a machine to calculate firing tables, although that was the crying need at that moment, but that after the war was over, they would have a tool useful in all kinds of scientific research, figuring out how big the little holes should be in the ammunition to make it burn properly, what granule size to use, and so on. So they and we agreed we'd make this as general purpose as possible so that it would handle any kind of a problem as easily as we knew how. That meant a lot of programming problems. As how do we set up different problems? And how much time will it take to set it up? And how general will our setup be so that there won't be any restrictions on what it can do? And so all of these problems were facing us, and all of them, you might say, had to have some kind of a decision before the machine could really be finished. So the first part, in addition to the first few months, in addition to consulting with the engineers as to what we saw as the goal for designing the components such as a counter and the modules such as accumulators and dividers and so on, we also had to think about those function tables I described, and we had to think about, well, how do you get and know what your accuracy is when you're doing a continuous problem with discontinuous or discrete variables. So Dr. Brainerd decided that a mathematician on the campus might help there, and so we did indeed get a man that was in the math department to come over and listen to this problem and work on it a while, and come back and report to Dr. Cunningham and some of the rest of us what he thought was the answer. Turned out that Dr. Rademacher, who had been primarily a worker in the theory of numbers, didn't quite have the right solution then, but by explaining further why he went back and worked out a solution which later another of our engineers verified it after the computer was built. Dr. Husky, who had a long history of working on other computers after the ENIAC, both in England and the West Coast. Dr. Husky, for a while, spent time with the ENIAC in verifying cases to which Dr. Rademacher's theory of how much round off and how much errors occurred due to the discrete nature of the calculation, the fact that you had to do it with a finite number of digits on a machine which couldn't hold an infinite number of digits. It's impossible. So we had those problems at startup. We even had another one there of a student in the math department, I guess it was, Tom Liberman, was set to work, I think by Brainerd, on this problem of what methods of integration for the equations of firing tables, equations of motions of shells, might be best for this proposed ENIAC. I had thought that a very simple method would be best, and that's exactly the kind of a method I showed in the original report submitted to Aberdeen. I thought that this was the way to do it, and here's a short, simple method, which was not nearly as complicated as some which were used by people trying to do numerical solutions of differential equations, rather. And finally, when Liberman came back from his study in the library, why, I had to lose a little bit of satisfaction because the method that I had proposed I had never seen proposed anywhere before. Short, sweet, simple thing, you know, just a step-by-step thing which used the tangents to the curve as extrapolated by one step. He came back and he said, well, in 18-something or other, why, a man named Heun proposed that. And so thereafter, everybody talked about the Heun method. And just recently, I asked some of the people who used to work on the ENIAC and worked for Aberdeen and so on, like Betty Holberton, well, when did you first hear about the Heun method? Well, that's what we always used. And everybody now thinks that the Heun method was known to everybody all the time. But I really believe from Liberman's investigations then that what happened was that the Heun method had dropped out of sight. Everybody had forgotten about it. And they were using much more complicated methods and other ways of going about these integration methods. And what I was proposing was they go back to a simple method, because although this meant more steps had to be taken, we would now have a machine that could take them so much faster. That was the simplest thing to do. And that's the way it turned out.
I think when you get to it, it becomes a little...
You too? You think it went in the basement?
Well, I read somewhere it was a bit 18. Well, how many square feet? 100. How many square feet was it? Did I read 300? No, 1,000.
Well,
1,300 or something.
Frankly, I never worried about these statistics. I have difficulty remembering just numbers as sort of uninteresting things, you know.
Yeah, but it must have been impressive, though. You've got to admit, it must have been huge.
Well,
it's bigger than my first house, I think. 13.
I didn't care how large it was as long as it did its job of computing. So, how large it was never impressed me, and
I'll have to get that from Kay.
how many miles of wire there were in it, for instance, that didn't worry me. How many soldered joints were in it. But somebody compiled all those statistics so that someone who would be interested in those things could be told. I don't know whether the newspapers were given those figures at the time of the dedication or not, but there are a lot of just plain, boring figures, you might say, about how many miles of wire and how many soldered joints. I was more concerned, of course, at the time with the fact that some of the soldered joints were not properly soldered. And so I spent all of one night practically on the floor of this room in the back of the Moore School, which had been a laboratory prior to the war. And all that night on the floor, trying to find what was the intermittent problem in one of these so-called portable function tables. Here was this large panel with switches sufficient to set 12 decimal digits on 103 different rows or something of that sort, so that one could cover more than 100 arguments, individual values of whatever, sines, cosines, air resistance, or what was called ballistic drag by the people at Aberdeen. Whatever function you wanted to set in there, why, you had to choose which function you wanted first, and then you had to say, well, what range do I want it through, and how shall I set up the table, because there you had, as I say, 6 decimal digits that you could set on each row. And the reason we made it that way was to give people options such as being able to put a 10-digit number in and maybe nothing else, or a 10-digit number might be more useful if you put in some differences in there so that you didn't have to calculate the difference each time you wanted to interpolate. So with only 100 different values of a table, why interpolation was expected as a frequent thing to do. And the controls for this table were such that they, upon request from the rest of the computer, would feed out numbers corresponding to 5 successive values, 5 consecutive arguments, and the numbers that fed out could, of course, be interpreted as whatever you designated when you put it in. That might be 6-digit numbers and have both these, for instance, a sine and a cosine. You might say, well, the argument is an angle, and the first 6 digits will be the sine of that angle, and the second 6 digits will be the cosine of that angle. Or there's various other ways. As I say, you could make some of those digits represent differences used for interpolation and things of that sort. And we therefore provided this row with, I think, 2 algebraic signs. You could make 2 quantities plus or minus in that row if you liked. And so with all of this option and choice built into the thing, why, the other feature of it was that here was something which would be a little slow in setting up, because you'd have to set all these switches by hand, and then you should have somebody proofread them, so to speak, check that you set them properly before you used it. And one way to do that proofreading was, of course, to have a program in the ENIAC computer which would read off all those values, and you could get them punched into cards and later printed, and then you could check against the printed values whether you'd set the switches correctly. And then, with all of that done, why, you still have the problem of maybe you want to change from one problem to another where you have a different drag function or a different something which you want to put in the function table. So we allowed several options there. One was that this table I'm talking about was on casters, could be rolled around the floor and plugged in to particular places which were the function table controllers. Well, if you wanted to, you could have 3 function tables, each doing its separate, different function, all working on one problem. But another choice was that you could only maybe use one function and have the other 2 tables rolled out of the room and have somebody out there setting switches for another problem while this one was being used. And so there were these various options open to the user. And the difficulty that occurred that caused me to lie on the floor all night was that in rolling these tables around on a somewhat uneven concrete floor, there was a little bit of torsion in the frame of the function table, and sometimes the function table would give out a different value than at other times. There was a contact in there which hadn't been firmly established, connecting these switch lines to the various cables which went to the main body of the machine whenever it was plugged in. Well, I found a drop of solder, yes, a big splash of solder you might call it, which had occurred when somebody was using a little too much solder in some upper part of that switch combination, and that drop had gone down to the base of the machine and lodged itself between 2 contacts on something at the base. And this, of course, was not a properly soldered joint. It was just a drop of solder which splashed there. And so as the torsion occurred in rolling this thing around, sometimes that drop of solder made a good contact between the 2 pieces that it touched, and other times, why, the contact was so poor that it, in essence, didn't exist. And when it did and when it didn't, how could you tell? It just depended on where you moved this function table to. So it took some hours to just going through everything, you might say, to find that. Well, that's just one example of what can happen in the construction of any piece of equipment.
And we're at the end of the tape.